All right, 7 o'clock. Let's get started. All right, today we are on review of lecture 9. This is searching and sorting. So these are quite common things that we do to the computer. Whenever we open up our computer, you either Google search or you do some kind of sorting to find the stuff that you want. All right, so all these are working on big data. Big data in general, like what you searching the web pages and so on, that you have things stored in tuple, or actually tuple is after you read it out from your disks or some permanent storage. And lists, both of these are dealing with big data. So I've mentioned this before, so let me just quickly run through them. So basically, if we are dealing with big data, you are doing these 5 things. You cannot run away. So searching, sorting, and we also have gone through some of this filtering. Basically, you see the record, and some of these records you don't want it, and then you can just filter them away. And you also do some calculation by taking a record and do some computation to it, applying some calculation like salary computation and so on. Accumulating, like what you do is finding out the statistics. What is the mean, the average? The mean is the average, and the standard deviation, all this kind of various stuff got to do with statistics. All right, and also you saw these things in lecture 8. Lecture 8 on this is a signal processing way of processing your data. So you pass from one to another and so on until you hit the result. So you can always pipe your answers from one stage to the next. And this is kind of interesting. You you can then do some functions and then do one after another. All right. So as I said, there are lots of all these higher order function. You don't run away with it. The upcoming the midterm. All right. You will see some of this stuff. No matter how I try to play with it, I cannot run away from these 5 types of things that I can test you. All right. So nothing to be afraid of. You try some of my past year papers, you will see some of this style already there. Okay, so this is dealing with big data. Sorting and searching are dealing with big data. So sorting and searching, what I meant, these are actually very important topics in our time. During my time, actually, we study sorting and searching in one full semesters. Basically, that means 13 weeks. We studied for understanding the time and space complexity. As you could have seen there, like this guy. This guy, you see that some of this that we talk about, bubble sort, I see so is damn slow. So slow. All right, when this is random. On the other hand, if it's nearly sorted, maybe it can actually be quite fast. All right, but normally in practice, we're dealing with random. So bubble sort is pretty slow. Selection sort is also slow, while the other kind of sorting, like merge, heap, shell, quick, and so on, they are much faster. Insertion is also kind of slow, because all these 3 guys are O of n square, and most of these guys are O of n log n. But there are some expectation, like quicksort, it depending on the pivot. And we also study this thing with respect to random input, when the input have no particular characteristics, or it's almost sorted, or it's in the reverse order. You see, some of this in the reverse order is quite painful for bubble sort. Or you have some few uniques, means that there are a lot of repetitive numbers. All right, so which are the good one? So in time and space complexity, you saw that we talk about worst case, average case, good case, and so on. So, for example, in a good case for bubble sort could be, things are almost sorted. Okay, then it will be done quickly. But if it is reverse order, it's quite painful for him. Random is also quite painful, and so on. All right, so this you will encounter some of this stuff if you study higher order, higher level classes. All right. So, but here we only have one lecture, so it's kind of limited. But at least you get a sense of it, and you can at least see some of this stuff. All right, to put you in a perspective, actually, until now, I mentioned this last week. We play with the code, we get good code, and then we get efficient code. And today, I want to take the opportunity to show you what it means by correct code. All right, that is the proof of correctness. I think this is the most difficult part, and this will differentiate you from those people who just program, because programming is not aga-aga. If the word makes sense to you, meaning that it's not roughly like that one. It has to be precisely like that. Okay, so there are also in real life, there are also I mean, in computer science, there are also algorithms which people allow it to give mistakes once in a while. All right, those Las Vegas, Monte Carlo algorithm, and so on, in these kind of aspects. But in most cases, we want things to be correct. All right, like of course nowadays in machine learning and so on, you see that some of these stuff are actually aga-aga, meaning that it's not always correct, but it meet the requirement most of the time. Now, in the traditional computer science, we actually needed to make sure that things are correct if you write a program. All right, so this was differentiate those people who are trained in computer science versus those who are just novice, just know how to write some program. Doesn't mean that you know what computer science means. You must know that there's such a thing as proof of correctness. All right, so those people who do not learn computer science properly, they will just know maybe up to here or even here. But at this time, I hope that you already know what time and space complexity. And today I'm going to show you a little bit about proof of correctness. Of course, proof of correctness is not a simple topic. Usually this occurs in higher level classes, but here at least you should get the sense of it from some of the examples I'm going to show you. And from there, you see the gist of it. And hopefully, whenever you encounter a program written by someone, a program written by yourself, and so on, you should be able to argue that why you are writing the correct thing. Okay, when you're writing the correct thing means that you're writing things which meet the objective, and also, of course, you have these assumptions that you are flexible. That if you must have met the assumption, then my program will be correct. Okay, so I'm going to show you some of this proof. First, let's do the selection sort. This is a selection sort. Here is how it looks like. Here are 10 numbers. Selection sort, basically, you go through the list of numbers and take the one out and then put it to the front in this case. Okay, so this is selection sort. So this is doing it by 16 is the smallest. Oh, now 0 is the smallest. Okay, so 0 is moved to the front. Next round. Now 9 is the smallest, and 9 is moved to the front, and so on. Okay, so this is selection sort. All right, and here is the code that I have for you. Okay, here's the code. This code slightly different from here. This one is swapping to the front for the smallest. My code here, okay, of course, I can post this as a question for you to prove the correctness. For me, I'm doing it differently. I do my selection sort in another way. So what you saw here is an in-place sort. What I'm sorting here is not in place. I'm using an extra array, in this case, my A list. Okay, so my selection sort, I'm going to sort this bunch of number. So in going through the number, I see 1 is the smallest, and then I will put this 1 into sorted A. And then I will see another one and put it into sort A, and so on. So here how it looks like. First, I make a copy of my code, my input B list, and my sorted list is empty at the beginning, while my A list, which is the same as the B list, is non-empty. Then I assume my smallest number. Okay, so here's an assumption already. The assumption is that the number that you have from B list never larger than this. I mean, never larger than this. So this is my initial smallest. Then here is the loop for me to go through all the numbers in A list to find the smallest. Then I remove my smallest from my A list and I put it into my sorted list. And at the end of this, I return this. All right. So this is the routine. It intuitively it should be correct. But why is it correct? So This is where computer science is so closely related to mathematics. And here I'm going to show you a step by step how we can argue that this whole thing is indeed giving you sorted A and this is sorted. All right, to start with, actually you must know when you're proving, you must know what you're proving. So let's see. Anyone want to guess what are the things I should be proving? You want to type it out in your chat box or you can just answer it. Anyone? If I want to argue that this program is correct, what must I prove that I do have? Anyone? You want to guess? No? Okay, here are the conditions I have to prove. All right, condition one. The sort A has the same set of elements in the input list B. Correct? This guy output must be the same as what I give you input. All right. And condition two is that the sorted A indeed is arranged in an increasing order. All right. All right. One is not enough. Two is not enough, but you must combine both. Is that okay for you? Give me a check if you're okay. Yeah. Okay. All right. Actually, in this, what I'm saying is not, it's still not enough, but that is a technicality. In fact, I should be also saying that this whole program would stop. All right. If this program doesn't stop, these two conditions is useless. All right. But this part I'm not going to show you. The missing thing is that the algorithm indeed terminates or not. We need this to archive to achieve the full proof. In doing time complexity, we're actually doing termination proof. So if you can tell me this time complexity, you are actually also telling me that this program stops. Okay. So I can actually skip this if I don't want to do it. Okay, so let me focus on telling you condition one and condition two. Okay, so here is how it goes. I'm going to do condition one first, then I will do condition two. So condition one, it's here, and I do have. I will get this. A list is the same as B list. You have no doubt about this. We have to trust that this copy is indeed copying exactly B list into A list. All right. And sort A is empty, meaning that sort A union A list is equal to B list. This should be okay for you. I take sort A, which is an empty set, and I union it with A list, which happen to be the same as B list. And so the empty set union with a set, which is originally equal to B set, the B list. So this statement is true. So this is the statement what we call invariance. I want to prove without the S. Invariant, meaning that it is always correct throughout my algorithm. All right, so I'm going to argue that. Okay, so this is 1.1, 1.2. 1.3, yeah, one, yeah, it is 1.3. 1.3 is here. What does this two do? This two thing is trying to remove something from A list and add that something to sorted A. All right, so in doing so, whenever we remove from A list, it is added immediately into sort A. So we can confirm that this thing is still true. This invariant that I talked about, right? Sort A union A list is still the same as B list. Okay, so this is my third. I wanted to end it up with sort A the same as at B list. That's what I'm achieving. Okay, so I just need this last step. This is a little bit difficult to because of the setting. Okay. All right. So before I return, once you exit this while loop, All right, exiting the while loop means that A list is empty. All right, you don't exit the while loop while A list is non-empty. You keep doing this thing. So as we always maintain that this it's the same as this. Since A list is empty, we now have sort A equal to B list. Condition one is fulfilled. Is that okay for you? Give me a check if you're okay. So at least now we have condition one fulfilled. Okay. All right. Next, we need to show that condition two. We want to show that condition two is such that the sort A is indeed in increasing order. All right. How do we do that? So here it's all the steps. So we do for element in A list, we do find out the smallest, right? So, right, 2.1, I mean, I use, to prove condition two, I use all the point one, point two, and so on. To prove condition one, I use 1.1, 1.2, and so on. All right, 2.1, A list contain all the numbers larger than those in sort A. All right, this is true initially as sort A is empty. All right, you cannot dispute this, right? Because sorted A, when it comes into the loop, sorted A is still empty. So A list has everything that sort A doesn't have. So of course, A list has all the number larger than those in sort A. Number two, sort A has the number already sorted before entering the loop. This is true as sort A is empty initially. All right. So sort A is indeed sorted at this moment. Then I need another one. All right, this loop is telling me to find the smallest guy. So once I have found the smallest guy, I have 2.3. At the end of the for loop, smallest is a number in A list, which is indeed no larger than all those already other guys in A list. All right, because this is going through everything in A list, and the one that you found in the smallest, it's indeed smallest than everyone in A list, or no larger than those in A list. All right. Then 2.4, since number in A list are all no smaller than those in sort A, the smallest we have found, it's still no smaller than all number in sort A. All right. So that is to say that A list is always larger than the number that you get smallest is actually still larger than everyone in no. We can say this. We can say no larger than I mean no. I understand if you assume uniqueness that there's no number repeating, then it will be easier to talk about. So the number that you got is always larger than those in sort A. So by doing append at the end of it, what you get is indeed added at the correct order. All right. So this is the next thing that you can achieve with this. All right. So 2.5 from here, smallest is now added to sort A. This condition maintains the order of items in sort A. Because this new guy that just got appended is no smaller than those other guy already in sort A. Okay. Therefore, for the very first time when it is removed and added to sort A, it indeed has the smallest from B list or A list because B list and A list are the same. Then from one round to the next round, that means because you're going through the loop, right? When it is moved and added into sort A, it indeed has the smallest. Okay. And we get the next number, which is still larger than those in sort A, and then added into sort A. So this maintain it. To sum up, it actually maintains sort A to be sorted, and on elements in A list still no smaller than those in sort A. So each loop that you go through, you take out something, and that something that you took out, it's always larger than everyone in sort A. And when you add it, of course, it's in the correct order. And the one that you took out is because it's the smallest. It's also no larger than everyone in A list remaining. And so you're okay. So this loop continue doing this, and you achieve this. And last but not the least, 2.8. Wow, 2.8 here. Since the A list is empty, because you get out of this, sort A is equal to this, and A indeed is sorted, condition 2 is fulfilled. And so everything is proven because of, so this last line, it's a combination of 1.5 and 2.8 to maintain that this is sorted. So this algorithm works, okay? As to how efficient or not, this is not efficient as you saw it, but that is not the point here. All right, so this is the proof that you have to do. I'm writing it in English. Actually, in programming languages, you can always use symbol for some of these argument. And I don't do that here for you. This is much easier to understand. Of course, it should still take some effort. If you need to review the video with 1.5 times speed to see how this is actually done again. You should be able to appreciate it. All right, any question? Okay, give me a check if you're okay. Okay. Okay, let me give you another one. I have a few. Whatever I cannot go through, I will leave it to you in the forum for you to check it out. So the next one is merge sort. Okay, merge sort is to divide the thing into two halves, and then within each half it does the work recursively, and another half it does the work recursively. So this is how it looks like. Maybe I use 20 or 16 is easier, maybe random. Okay, so sort, so the depth. So you can see how it, you see it divide by, and then you sort within there, and then merge with the other two. These two has to be sorted first, and they are indeed sorted. All right, then they are merged. All right, so these four are sorted, and then these four has to be repeated. And once they are sorted, then they will be merged with this guy. It happened to be sorted, but the computer doesn't know, so it has to go through the motion. All right, now these are sorted. We go up to the next level, and then now 8 of them, they are sorted by merging. Okay, so here it's here's the code. All right, the code says that merge sort, and if the length is less than 2, you just simply assume it is sorted. Of course, right? There are only one item or no item. And then the left, it's recursively sorted. The right is recursively sorted. Then the magic comes from the merge. Right, this is merge sort, this is merge. So left is sorted, right is sorted, you have to merge it. And how do you do merging? You do merging by assuming the result is empty. Then you look at the left and the right. If the left is the first guy is smaller than the right, then you append the left guy. Then you remove the left guy. And if the right is smaller, then of course you append the right guy and you remove the right guy. At the end of this loop, it's either the left is empty or the right is empty. All right. In any case, you just extend it. If it's empty set, you extend nothing. If it's not empty, you extend it with a number. Same for the right. So it's symmetrical in this. Okay. So this is how the sorting that you saw just now. Okay. So the same thing. How do I prove that this is correct? So there are two conditions that I need. The two conditions are that condition 1, the result has all the element in the union of left and right. Okay, you don't want to miss out any guy. And number 2, elements in the results are indeed sorted. So maybe I should put this here because we only need to care about the merging. The recursion is assumed sorted. This is proved by induction, if you know what that means. Most of you should because it's normal mathematics. All right, so these are the two conditions that you have to uh, prove. All right, so the first thing you have is how do I want to prove condition 1. All right, so my result is empty. So I want to argue the following. The left is sorted as given. All right, left is sorted by induction. Right is also sorted. Right is sorted with smallest in the front. So the 1.1, it's that the result, which is empty, union the left, union the right, is equal to the input left and union the input right. All right, this is I want to differentiate a little bit of the left and the right with the input left, meaning the original left and original right. So this is the original, okay? And the union of the two, of course, is empty set union originally, okay? So this is 1.1. I want to maintain this always. So 1.2, okay, let me see. Okay, here. My 1.2 comes from the fact that I have to make alteration to results and left. So I append something and I remove something. So it means that I have to argue what happened after the change. All right, append to result follow immediately by removing from the left or the other way around. Okay, I can swap the two statements. All right, and so we maintain the result, all right, which is now added with one item, union the left, which is the new left, because the left has been removed. Union the right, which is no change, is still the same as the input union and the input right. Okay, so and you would have the same argument for symmetrical case 1.2a. All right, this is symmetrical case. Okay. Then at the end of this here, but we have at this point we still have result because at the end of it, you get out of it, you still because it's always true, either this case or this case, each time you go through, you always maintain this statement is true. All right. All right, so this statement remains true once you come out from the for loop or the while loop. Okay, so and then I also make changes here. You extend. Oh, okay, maybe all right, so I can change this code a little bit. So it looks like this. This one is just simply do the left, extend it, assuming the left is non-empty. This one is assuming the right is non-empty. So I could add the condition there if I want to. All right, so I don't want to do this. If the left is non-empty, this means that the right is empty. This also means the result has all the elements from right already. Then the 1.5, the result union left union empty set, which is the right, is the union of input left union input right. Now we put everything in left into result, so result still become like this. So the result has this thing. So if this is not true, then the symmetrical case it's happening. So let me just put the symmetrical case here. All right. Otherwise, the right is the 1, and you symmetrically 1.4a, 1.5, and so on. Okay. And so the result is such that I do have. So at the end, this result fulfill my condition 1. All right. So the result is input left union input right. In either case, condition 1 is fulfilled. Okay, so this is to prove that the condition 1, the result, that means that the result you return must have all the elements from the input left and input right. Okay, this is the input left and the input right. Okay. Next, I need to prove is the element in the result are indeed sorted. So where are things happening? So here are things happening that I add things into the result. So I must argue something. So to start with, I have When I enter the loop, at this point, when both left and right are not empty, so we can have left 0 and left right, so we can enter it. Then we also know that left is smallest of all elements in left, and same for right is the smallest of all elements in the right. Okay, this one is establish this fact first. Then I have this other thing that I do when I do take append the left to here, because I know that the result left is smaller than result right. So of course, if the left guy is smaller than all the guy on the right, or the first guy on the right, of course it's then smaller than all the guy on the right, and itself is also the smallest among itself on the left. So by putting him into the result, there shouldn't be anything wrong. So this is what I meant. Okay. So this means that left 0 is the smallest among all in left as well as in right. Then this is to add the smaller into the result, while this is still larger than all those added into result earlier on. In saying so, we are asserting that the result is sorted with a new addition and new guys that added. All right, the number in the result are still no larger than those in left and right through each loop. All right, so you get a sense with similar to the case of the selection sort, and the other half of the story is the same. So this is the same. Let me just type this part of the story. It's the case for the right, so symmetrical. And then up to the end. So before I enter the loop, enter this one, I have also result remains sorted in increasing order. Also, we know that either left or right is now empty. All right, because you get out of this while loop, one of them must be empty, or both of them is also empty if possible. In that case, maybe I have to change the code. Else, if I don't have to change the code. Is if it's empty of left, left is not empty, I do it. I know that then right must be empty. Otherwise, if left is empty, then I do. If right is not empty, I do it. Otherwise, I don't do anything. Okay, so I'm okay. So this is 2.5. Then I have 2.6. Okay, result remains sorted because it's extended with those numbers in the left that are sorted already, and those numbers are actually larger than those in the result. And then there's symmetrical case there. So the final result here is coming from both the left 1.6 and 2.7. All right, so this is how this is proof, and this is the proof for merge sort. All right, this part is through induction, that smaller set evokes smaller set evokes. So both of them are sorted. Then a merge is doing its job, and therefore the whole thing is correctly done. Okay, so this is merge sort. You okay? Give me a check. All right, maybe I have to say that this may looks a little bit scary. That the kind of thing that we have to say, and some of this stuff may look obvious, but actually they're not. Like when you are in the when you are young, since young, you do all this. Actually, you're doing proof. But here the proof is now written in English. You need to know a little bit to get some sense of what you are actually programming. And so far, some of these programs that you do, for example, this one, all right, this will be down to earth to you. You do this. Now, why would you believe that this is correct? Okay, this is coin change. If the amount you have is 0, then there's only one way you can do it. All right, that means you don't use any coin. Okay, if the amount is negative, you can't do anything. It has to be a 0 way to change it. If the number of coin you have is now 0, of course, there's no way that you can do any change. Okay. And otherwise, this is a recursion. You actually do coin change with all the coin. Okay. and use one of the guy to change it, the last guy, and use all the coin, or you don't want to use the last guy and you change the amount. All right, so this is complementary to each other, and the sum of the two give you the answer. But why is it so? Actually, this is also a proof. Let me just quickly show it to you. So this is the proof, and this time is a proof by induction okay. So base case all are correct. Okay, I have already told you 1, 2, 3 cases. And proof by induction. So this one is assumed to be correct. So this statement is assumed to be correct. So this statement is saying that you want to change using n coins on this amount. All right, that is what this one says by proof by induction. And so this is correct. And what about the second statement? The second statement says that it's the number of ways to change A with only n minus 1 coins. That means missing out the last one. Okay. And then why the sum of them is correct. So here is the argument. The argument is that the number of ways to change amount A with n coins is the sum. All right. This is a pure logic that this is has to be believed. The number of ways to change amount A without the coin of denomination n plus the number of ways to change A with one or more coins of denomination n, right? All right, so A doesn't include anything in B, and B doesn't include anything in A. So the complementary to each other. You're not overcounting, you're not undercounting, and the sum of them is exact count. All right, so this has to be true. And then how do you get these two? So indeed, by induction, all right, A is exactly this formula, okay, which is this one. And B is exactly this formula, all right, and which is this one. Therefore, the needed number is A plus B, which is as specified. So this program is correct. All right, so this is how, even though this looks very innocent, and if you really question us, we should have given you this kind of statement to supplement, to convince you that what you're seeing is correctly done. Okay, and this one you can ponder about it. Then let me give you another one. Okay, this one is credit limit that you saw last week in the recitation. All right, this note. Okay, you're supposed to implement a improved version of credit limit that will return a schedule with the total number of units is less than or equal to max credit, but you want to have maximize the number of causes. All right. I alluded to the fact that actually this question is the same as the solution, as the same as the coin chain. Indeed, here's a solution similar to the coin chain. So your total credit is actually you calculate for the schedule. All right. If the total credit is less than the maximum credit that you are allowed, then of course the schedule is valid. You are done. If the maximum credit is less than 0, that means that you don't have any credit to use, then you cannot do any courses. So you have to return none. But otherwise, all right, this is now you see sounds like here. Otherwise, you do schedule 1. Schedule 1 is to drop the first cost. And then schedule 2 is to without dropping the first cost. Okay, but you use the first cost already. So this is using the coin. Here is using the cost. Here is not using the coin or not using the cost. So this schedule come out by induction, and then you see which one is better. If schedule 2 is and now then schedule 1, of course. If it is schedule 2 is viable, need to add the first cost back. All right, then schedule 2. All right, if schedule 1 is none, then return schedule 2, and both viable. If both of them are okay, then you will have to see who is longer in terms of number of causes. And so you compare, and if the longer is schedule 1, longer or no less than, you schedule 1 at the west schedule. So this is the same as this, at least this part of the rationale or the reasoning is the same as coin chain. You use it or you don't use it. And at the end of it, there's one additional step as to compare the length of the one of them versus the other. Who is longer? Can you use it? Okay, so the proof of this guy is going to be the same as this one. Now, I have a little bit of time. Let me show you the last one. Okay, last week when we talked about the solution of this, I didn't actually talk about it in this manner. I give you this code. Okay, I give you this code. How does this code work? The first line is the same. The second line, while loop until the end. What do I do? In this while loop, I go and find out who is the largest cost in with the credit. And then I'm going to drop that guy. Okay, and then my new schedule is the one without this guy, this largest guy. And I continue doing it until my total credit is no larger than the maximum credit. Basically, I'm doing like some of you does, some of you do that by sorting and then keep only the front, all right, or you by sorting, dropping at the back, those larger one until you have you don't need to drop anymore. It's the same. All right. So I avoided the sorting. As I told you, sorting could cost. And of course, it doesn't change the time complexity, but still, you can avoid sorting. Usually we avoid. Okay. So about this proof. So the rationale of this proof is rely on the fact that the solution that you have should be those of smaller credit unit. Okay. So here is the proof that I can roughly show you. This is the algorithm that we talked about last week. So my solution is next smallest credit unit and so on until we can't include. So basically there are 4 ways that you can do this. You can find the largest to drop it, or you can find the smallest to include it. All right, that's one way. There are 2 ways here now. And then the other one is sorting. Sorting by you sort it, and then you keep the smallest until you cannot keep anymore. Or you sorting, and then you drop the largest until you cannot drop anymore. So here is a proof that it's one of the few. It looks like this. All right, this is called proof by contradiction. There is only a solution. Suppose there is only a solution X that has all these causes, X1 to Xk. Not all the smallest credit unit costs are included. All right, because our premise is that we must have a solution that includes all the smallest credit units. Okay, if it doesn't, that means I'm trying to contradict it. All right, so and the following argument is to show that if it doesn't, and then I'm going to change you, and I can always add the smaller guy into it. Okay, I will. So roughly speaking, it's like this. So you can assume that there is a credit that are sorted in X1 is the smallest in credit. This is a standard thing in mathematics without loss of generality. You can assume that the solution you have X, capital X, it's smallest, larger until the XK. So XK is the one that has the largest. By contradiction, we assume that we have a cost called X that has a credit limit smaller than XK because not all are smaller in this solution. Then we can drop him, we can drop K and use X instead. And then 2 things happen. Number one, X is the same number of causes because we drop one and add one. Number two, the total credit limit, the total credit is no larger than what originally in X. Therefore, X prime is also another solution. Then this is another technical word, extremal property to say that you can keep doing this thing until it doesn't happen, and which is the case that this solution is not true. I can have a solution as what I program it to be in here. Okay, I will leave this thing like that, and you can check it out. Maybe I will put the whole thing into the forum. Of course, at this point, it's kind of confusing to you that, here I use English, all right, to tell you the program. So this is proof specific to the program, all right? And in a lot of time, technical papers that you read, you don't see proof according to the program because they will assume that you know how to write a program. Okay, you need to know you know how to write a program according to the concepts. So here is the concept. The concept is that you must have a solution that you can include only the smallest courses, smallest credit courses. Okay, and therefore you have this kind of proof. So or whatever it is, then you may ask, what is a proof? Actually, I wanted to tell you that, and I'm trying to convince you that you have been doing that since young, but many of you may not agree. All right, so let me just round it up. All right. So, for example, in young, you have been doing 1 plus 2 plus 3 plus 4 is indeed 10. But how do you get 10? Actually, what you do is 1 plus 2 is 3. Okay. Then 3 plus 3 is 6. Then 6 plus 4 is 10. So what you're doing is actually a step by step. And each step you convince people that it's correct. Okay. Because I believe you 1 plus 2 is 3. And I believe you 3 plus 3 is 6. And I believe you 6 plus 4 is 10. Why do I believe you? Each of these is a truth. I can use a lot of ways to count with fingers or whatever. Okay. All right. So all in all, actually, proof is something seems scary, but actually it is just a series of statements. And the proof is such that it's a series of statements, and somehow it actually wrote it in a manner that it's written in a manner that is concise and it fit within a small space, just like program. And to convince people of all the possible cases that you could have, it's all covered in this short description of things. All right. So proof is only a series of statements that concisely present. We need to organize a little bit on what we want to do with the statement by statement. All right. So it means that you have to be careful, just like when you're writing program with a lot of if cases, you must know how to reorganize it like the leap years. If you know how to organize your code, the code may be just 3, 4 lines only. If you try to be verbose and you state every cases explicitly, then you will have a long page. Same for proof. All right. A proof is that there are many cases, but actually, I can actually concisely or summarizes it and present it to you within a page, that kind of thing. Okay. So that is a proof. A proof is a series of statements or arguments where each statement follow from some previous statement or some known facts to cover all the case or cases, situation we are interested in for the problem on hand. All right. So this take a lot of guts to really believe this thing and a lot of experience in proof, then you will know. Anyhow, at least after today, you should see got some sense about proof. I will not ask you to write a long proof in our assessment, but I will may ask you to give me an indication that what are you proving to make things work out for your code. Okay, and there are many kind of code proof actually. I only show you proof by this is induction, and then here proof by contradiction, and they are proof within the program, and there are actually many proofs. They are proof by existence, but there's one thing that you should know that is not a proof. Proof by example is not a proof. Okay, so that one you always say I run some example, hey, it works, but actually that are not proof that your program is correct. Right? I will just want to sum up that the mathematics here actually play an important role in computer science. Okay, so today you get a rush course, a crash course on proof, but not to worry too much, just get some sense that what you are targeting that should do. Okay, I'm done with my review. Any question? Yeah, okay, give me a check. Okay, thank you very much. Let me see whether Juni is here. He's not. He should be here in a short while. Let me just remind you about the midterm. What's my midterm? Okay, the midterm. So you have to give me, if you have any official duty, you have to tell me before 21st of March. Otherwise, we assume everything goes as planned. MC has to be submitted if you happen to be sick, hopefully not. And then by noon that day. Junyi, are you here? He's not here yet. But you have any questions about proof, you can just post it or you can ask. Oh, by the way, the assignment for the grouping are here. I believe I've honored all your requests. If not, then you can send in your request and I will check against your review. Oh no, sorry, your survey. Then I will change accordingly. All these names are already submitted to the school. They will be put into the canvas. He's not here yet. Just wait a while. I need him to take over. Anything you want to ask about the midterm? Yeah, okay. Okay, he's here. Junjie, you're here.
Yes.
Okay, let me make you the host. Okay, you take over. I will leave. You start at 8.
Yeah, can.
Okay, I don't stop the recording now. So the recording is on. Okay, bye-bye.
Bye.
Bye.
Right. Hi, everybody. Can you guys hear me and see my screen? Right. So it's 8 p.m. I'll start the tutorial now. This week's tutorial is tutorial 4. It's on higher order functions. All right. So question 1. So we're introduced to the composite Simpson's rule. So it's a math formula, which is like a method to do numerical integration. So you can watch a YouTube video about composite Simpsons rule if you want to know more about the math side. But here we'll be tackling the programming side. So this is a formula. You got H3 and a lot of terms with a kind of pattern, like from 1 to 4 to 2 to 4 being times to the y term. So you have all the information here. H is equals to b minus a. So you have to incorporate all this into Python. So can I just see your answers for calc integral? Right, I'm going to look for some interesting answers. See if you all did it any other way other than iterative. Right, let's go through your answers first. So most of y'all, actually, every answer I see here is basically the iterative method. So let's have Bruce explain your solution. Bruce Samuel. Hi, Bruce, are you there?
Hello, hello.
Hi.
Okay, first I find the H. The H is provided. The formula to calculate H is provided in the question. Then I create a higher order function called YK. So YK is supposed to be in the formula either Y0, Y1, Y2, Y3, Y4 accordingly. So first I start by setting the result to be the Y0 value. Then I loop from 1 to n plus 1. Then I uh, then I add in all the Y0, Y1, Y1, Y2, Y3, Y4 accordingly. So for those Ys that are odd number, example y1, y3, y5, and etc. It's 4 times the y value accordingly. And for even numbers such as y2, y4, y6 is 2 times the y numbers.
Yeah, thanks. All right. So looks like most of you got the answer for this question. So as you can see, yes, this works. So I think none of y'all actually try a recursive way. If not, y'all can like raise your hand and show. But Okay. Oh, this is impressive. I was gonna ask somebody if they could use sum, but actually Asher used fold. So let's see. Yeah. Well, Asher, Yan, can you explain how you use fold?
So I did a recursion. So for each recursion, I will give out one term in the for. So I have a few functions to do which I define and calculate integral. So the first is the multiplier. So if x is divisible by 2, for those term numbers, it'll be multiplied by 2, and if not, it'll be multiplied by 4. And then for 4, each term will be the multiplier of the term number multiplied with the function, which is k y, the lambda function, which I use to calculate that y, and then it will keep recurring. Then I just added the yn at the back for the total, since there is no it's just yn, it doesn't have any 2 or 4. So that will be the total, which I multiply with h divided by 3.
Oh yeah, thanks. So I noticed you actually redefine fold here. Does it still work similarly to the lecture define fold?
I think this is just a recursion. It doesn't have the operator. It's just addition.
Oh, basically you just fix the operators.
Yeah, the
So it's still
operator.
the same as basically using fold, just that you actually hard coded it already inside. But it is a good attempt to use fold in to do this question. Because in exams, right, for some of the lecture functions that you have learned, like sum, accumulate, and fold, it's very possible that we have a question where like they first ask you to write the function. So let's say this actual question were to come out, okay, it definitely won't come out this exact question. But let's say a question like this comes out and you write your calc integral. Then the next part, the harder part, will basically ask you to apply fold. So basically like they'll ask you to write the function itself and just fill in what it will take to use the function fold. So basically you don't get to, hold on, turn off my, you don't get to write anything else. Okay, maybe you can write some functions, you can define some stuff up here, but you have to write in what are the inputs to the fold function. Yeah, so that's quite a common question you will see if you've been going through the midterms, you've been practicing the midterms. It also come in finals, so it is very good for you to learn how to use fold, sum, and accumulate to solve all sorts of different problems. So if you want more practice with that, you can go through the work bin on cosmology. We have all the past year midterms on it. So we actually have all the midterms, the past year midterms, but you don't have to go through all of them. Just go through however many it takes for you to feel confident if that's what you want to do. I'll show you how to use sum here. So I wrote it somewhere else. Okay, so here is the way to use sum. Just type it out. So how this works is, okay, you got the h calculate the h using the formula they give you, and you write a helper function term that actually finds the term according to the I. So it follows the same logic. So if it's the first or last, term, then you're gonna return yi. Else, if it's an even term, then you return 2 times yi. Yeah, to define yi equals to on the f function. else it will be an even term. I mean, else it will be an odd term, and you just turn 4 times yi. So you just define a simple combiner, or this is your operator, yeah. Now, add one is the next function that will be passed into sum. So for your sum, it takes in a term A, next, and B. So when you want to solve a problem in the exam using a call to sum, this is what you need to write in the exam. You need to write the inputs. What are the inputs? And if anything, any functions you need to write before the call, you can also write that in a separate box. And times that by h divided by 3. Okay. So this will also return true. So this will also work. So be sure to practice this sort of questions. These are one of the harder questions that could come out. Basically just adapting a question you already know how to solve, but using a call to sum, accumulate, fold, or any other function that you may have learned in previous lectures. All right, so we move on to question 2. So question 2 is very similar. It's another math concept that you have to write in Python. So write a function gk that solves the following product. So this product is makes use of a big pi notation, which basically is like sum, but it's like product. So it's a product of everything, all the terms. So can I see your answers? The question expects you to try to use fold to solve this problem. It's also possible to solve this problem without fold, but that would be trivial. So using fold to solve this is like applying a lecture taught function. All right, we have a lot of answers coming in. Ayan, Khalid, can you explain your solution?
Hi.
Hi.
Uh, okay. Essentially, the operation is you multiply the consecutive terms together. So you got lambda xy, then x times y. Then after that, the the function is basically what the formula written in the question, the x minus x plus 1 square. So I just I replicated it with the letter G. Then after that just put K because the sum is until K. Yeah.
Yep, thank you. So yep, that's correct. And this will pass all the test cases. Okay, let me see whether anybody else has a different way of writing it. All right, I noticed another way we will write this is it's like that. You define the operators like this, like in function. Just be sure that this is also possible to write in the exam. Because you can just write this in the box before the call. So you define your operator. This is the actual operator that's being passed into your fold call. Also, understand how to write using lambda. And a box that will, for you to write your operator first, and then what is your F, what is your N. So usually if you write it with lambda functions, it will be a more elegant solution. But if you can't remember the syntax for lambda function, this will work also. But make sure you understand how lambda functions work, because that can come in exam also. All right. Let's see if there's anything else. Okay, so that's basically the two different ways people wrote for this question. All right. If there's no further questions, we can move on to question 3. Okay, question 3 is a rather difficult one, particularly question 3b. So let's go through question A first. So we show that sum is a general case of a still more general notion called accumulate. Yep. So these are two functions that you've learned in your lectures, sum and accumulate. So what we want to do is write the accumulate function. So can I see your recursive solutions to accumulate first for 3a? All right. So there's not much a variety on how you can do it for the recursive way. The recursive way is rather simple. So let's have Debansha Das explain your recursive solution. Hi, Debansha, are you there?
Yes.
Yes, can you explain your recursive solution to accumulate?
Okay, so my recursive solution, I just named it. My recursive solution, you just need to do a sum from B towards A. Okay. Sure. So first we have our base case, which is that if A is bigger than B, then we can just return the base case itself. If now what we do is that we combine our first value, which is A, then you combine the first term A, with the rest of the solution, which is what we already generated from beforehand. And what this is accumulate with the next value of A, and rest of the terms are all the same. So yeah, so this is a recursive solution because we start from the base, which is our last value of A. Then we go backwards, adding each previous term A and going backwards again and again.
Yep, thanks. So let's see. Yep, this passes the test cases. So, so as you can see, the recursive solution follows the output exactly. So you can see here the math representation on how the function will be called. And this is when we print out using like print statements and some tuples. This is the representation on how the coalescing, how the operations work. So like first we plus together 5 and 6, then we plus together that result with 4, and plus that result with 3, and plus that result to 2, and back to 1. So this is exactly how like normal simple recursion works. So because we have combiner, okay, so let's say we use a simple combiner, which is addition between the term on the left and the term on the right. So term A is the first thing that's going to be evaluated. So term A, our first term would be 1 for this call. Will be 1, and this entire thing is generated by the first recursive call to accumulate. The first time we recursively call accumulate after the actual original call. So this was the original call to accumulate. Accumulate will recursively call itself multiple times, right? So the first time that happens, this is what is evaluated, and so on and so forth. This would be the second term generated, and this is the second recursive call to accumulate, and then third recursive call, and then last recursive call, and then only then will Python start to collect everything together in this particular order and this particular way of brackets. Yeah. So it will be a little bit different if this call to accumulate had been on the left and term had been on the right, because as you know, Python will evaluate your steps from left to right. So this is how you trace it. So notice that, let's say, had I had swapped the positions of term A and accumulate, watch here. See, for non-commutative operators like addition is non-commutative. That means if you do it in any order, it won't matter. Or even if you do it in different orders with using your brackets, it won't matter. But for commutative operators like your minus and your divide, it's going to make a difference, right? Because like it cares in what order you do your subtraction, or especially if you do it in brackets. So this is if your accumulate call had been on the left. So as you know, Python will evaluate everything left to right, and this is how everything collects. So this will matter more for the recursive way. I mean the iterative way. So the iterative way will have to copy the exact logic of the recursive function. So this will be the harder part. Okay, before we go to that, let's show how sum can be defined as a simple call to accumulate. Yeah. Because accumulate is a more generalized version of sum, right? Sum basically hard codes the operator, the combiner, as an addition. So let's see. All right, there's basically only one way to do this. Okay, for Rohan, okay, can you explain your solution? Rohan Gata.
Yep. Yep. So for sum, the right side is the same. The combiner function is lambda xy and then x plus y. So and then the base is 0 because starting from 0. If it was multiplication, it'd be 1.
Yep. Okay, so the other inputs are the same.
Mm-hmm.
So yeah, okay. This part. Yes, it works. Okay, thank you. So now let's go on to the harder part. So this is the iterative solution. So most people will actually like try to come up with a solution like this. Maybe this will be your first attempt and then you'll get it wrong and then you wonder why. So let's see your answers for accumulate iter. Right, I see a lot of different ways to do it. So this is the most typical way that we are expecting. Right, Yansu Tan, can you explain your solution, your iterative solution to accumulate iter?
Hello.
Hello? Yes.
So first I made a list, then I appended it with the term as long as it's less than or equals to b. Then I use the next function to go to the next a. Then I use the loop but in reverse way. Then I combine them together.
Yep. Okay. So thank you. So this is one of the ways we're expecting for you to do this question. So the reason why this solution will not work is that you basically are doing the operations in the wrong order, right? So what we are expecting, one way to do it is to first collect all your terms first generate all the terms using your A and B, and using the next function to keep getting the next term from your A index to your B index using term, and next to move on to the next index. So first you collect all your terms in a list or any data structure. This could be a tuple, assuming if you all haven't learned tuples yet, but if you all have learned lists also. So this works the same way. It's a data structure that you can keep elements in. So you first generate all your terms, keep them in a data structure first, then reverse the data structure. So the reverse function basically takes an iterable and returns a reversed object, which is another iterable that basically contains the original elements in the reverse order. And since they're in the reverse order, you can basically for I in this data structure and apply the combiner in the correct order. So one thing to note is even if you were to switch your order of term A and result here, it still won't work because you need to do the entire collecting of all the terms in the opposite order to achieve the same logic as the recursive function. Yeah, let's see if anybody else had any different ways of doing it. Okay, we can go through this way. All right, Isaac Lam. Okay, can you go through how your version works?
Hello.
Yes.
Okay, so my one, by going through the while loop from A to B and then collecting all the terms in a list. So then you'll have the full list of every term that needs to be combined. And going through the loop from backwards, you then add it to a total that's already been initialized with the base case.
Yep. Okay, thank you. So this is another way you can do it. Instead of reversing the list that you kept your terms in, you can iterate through the list in backwards order. So make sure you know how to do both ways. You need to understand both ways. It's best to understand all the different ways you could do it. So you should look through all your classmates' answers and see how all the different ways that everybody thought of doing it. All these should be valid ways. Right. But since we don't have that much time, I'll just show you a visualization on question 3. Okay, you could also use Python Tutor for this, but I actually made slides for this, so I'll just show you the slides. So if you cannot understand why we had to do the iterative version in such a way, so I'll show you this. Okay, so over here we have the accumulate function. So here I'm defining the inputs that I'm going to use. So the combiner, I'm going to use a simple addition function. So lambda xy takes two different terms and adds them together. So this is our simple combiner. It just does addition. Term is a very simple term. It literally just takes the x and just returns it. So we're not doing any transformations to it. The term will take the current index and return the actual index as the term. So very simple. Next, we are just going to increment the index by 1. So this is our call to accumulate that I'm going to demonstrate to you. So these are the inputs. So the reason why I saved it as com is because so it won't be super long and very hard to read. So I initialize the variables here for just so it's easier to visualize. So just remember com is our combiner, our simple addition. Term is our simple identity function. Just returns the current index. Next just returns the next index just by incrementing it by 1. So this is our first call. This is our normal call. So this is the first step of what happened. So obviously accumulate over here, you return combiner with term, the first term, and the recursive call to combine to accumulate. So when this is evaluated, so term 1 will be evaluated as 1, right? Next one will be evaluated as 2. And then when you evaluate this line, combiner, the next step will be 1 plus our recursive call. So we'll go on. This call to accumulate will create 2 plus our next call to accumulate. As you can see, next has increased our A, the A in the middle of the calls. Now A is equal to 4. We have added 3. And take note of the brackets. So this bracket order is very important for non-commutative operators. So now we've reached A equals to B. And now finally, this call to accumulate where A is equals to B is going to return our last term, 5, plus this call to accumulate where A has now become more than 5. So as you remember, when A is more than 5, you get the base case instead. So now we return this. So this is basically what happens, and we get 15. So here's a case where we have term equals to the square root 2. So very similar. It's a very similar way of the operations. So instead of the very simple term that just returns the actual index, we actually return the square of that index. So this all of steps is the same thing. So let's look at what it would look like if we had a non-commutative operator. Here I have for my combiner, I'm using x minus y. So this is the lambda function that takes in 2 terms and returns x minus y. So this is how it will be different. So this is how you can trace it in exam. So actually, when you get a call to accumulate and you want to trace it step by step, basically following how Python will evaluate it as an expression, you can write it out like this. Okay, the thing keeps pushing me back to the other desktop. But okay, so you can read like this. The call to accumulate, where we use this new combiner, this non-commutative subtraction. The first step is basically combine term 1 and this call to accumulate. And as you go down, this is we are evaluating it step by step. And notice how we have the same bracket pattern, but now the operator is non-commutative, right? So when we get our result, this is what you should visualize. Yeah, and that's why we'll get 3 instead of the other way if you were to write the wrong iterative version. Okay. So now back to the tutorial. Okay, question 4. Okay, so question 4, point can be represented as a pair of numbers, the x coordinate and the y coordinate. So here we are basically making an abstract data type using functions. So can I see your solutions for this? We want to create a constructor for a point, make point, and 2 getters that basically extract out the information from our abstract data type. So the abstract data type is a representation of a point using functions. And we have more functions to get the inner details of that point. So x point returns the x point and y point returns the y coordinate. So yeah, I can see your solutions over here. So you can either use tuples, or since you all have learned lists already, you can use the list version. Okay, not much to go through here. Let's see. Oh, okay, so some of you have actually came up with some elegant ways. Okay, this is a tricky way using returning lambda functions. So all these 3 ways will work. So this first way, points are represented with tuples. Or rather, I should say the underlying data structure is a tuple. And for this solution, our underlying data structure, which we use to represent a point, is a list. And here, the underlying data structure for our point is a function. So there is a lot of different ways you could use Python to create your extract data type, but however way you use will affect your further on getters for the next part of the questions. So even between tuples and lists, as you guys know, the difference between tuples and lists is tuples cannot be mutated, right? So you may have to take that into consideration for further getters and setters, especially for setters, because setters are supposed to change your data, right? But if your underlying data structure is immutable, you won't be able to do that without returning a whole different point. So let's move on to part B. Okay, so no matter what way you use to represent your points, you have to write. You need to create a representation for line segment. So you need three functions: make segment, start segment, and end segment. So can I see your solutions? Particularly those who did it using the tuple method, the list method, and the function method. All right, okay, so now I'm seeing a much larger variety of how you guys implemented the question. Okay, let's see. Let's go through the simpler ones first. Okay, so Kayang, how did you implement your segment?
I just like use the start point is 0.1 and end point is 0.2. Then I just use the functions given to return whatever is asked.
Yep, so basically you represented your segment using tuples, right?
Yeah.
So your constructor, so this is what we call a function that creates our extract data type. It's a constructor. So make segment is a constructor. It returns our representation for a point, which is the extract data type. I mean, the segment, which is the extract data type. So start segment and end segments are getters because they extract information from an instance of our extract data type. So since Kayang used tuples for his representation of segments, he can simply index it. So it will be the same if you were to use list in your implementation for your segment type. But if you had used tuples in your points, it will make sense for you to use tuples in your segment. So like to keep it consistent, you don't want to use that. Or you could use tuples in your point and list for your segment, but that's for you to remember. It will complicate the way you implement your getters and setters for all the various ADTs that interact with each other. So point methods and segment methods. All right, let's see who wrote this. Fine.
It was me.
All right, and can you explain how you implemented your version or segment?
Yeah, so I use a function. So if the value passed in the getter is 0, then it'll return the start of the segment, and then if it's anything else, it'll return the end of the segment. Yeah, so for the getters, you just pass either 0 or 1 to obtain the start or the end.
Yeah, so can you explain to like some people who may not understand like how exactly does the implementation work? So your segment is a function, right?
Yes.
Yeah.
So it's a function, and then there's a inside the function there's an if statement. So if the value passed is 0, then it'll return the start segment, which is 0.1. And then if it's anything else, it'll return 0.2.
Yeah. Is this the same way you implemented your point also with functions?
Oh yeah, it's the same way.
Yeah, okay. So this is an elegant way also. It's a very cool looking way. So you don't necessarily have to implement your ADTs this way. Actually, there's a much better way of implementing ADTs that we'll learn in the future called object-oriented programming. So basically, this is just to show you how Python works, that you can implement your abstract data types any way you want because they are abstract. So particularly this way of representing a segment as a function is a higher order function. So your constructor itself took in two inputs, the original points, right? So it took in the original points as its inputs. That means the return of this constructor will be a function that already had memory from its inputs. So you remember what inputs it had to this called the make function, to the make segment function. And this function that is being returned remembers what P1 was in its original call and P2. So when you had, let's say, you created a segment S1 using make segment P1 and P2. So this S1 will remember your P1 and P2. So when next time you want to call a start segment on S1, basically that will call the original S1 with input 0, and that's how you get the original P1. Yep, this is another way, so it's very similar. So who wrote this?
Hi, I wrote this.
Fine. Okay, so can you explain how your one works?
Okay, so my solution is similar to the previous solution where using a higher order function to inside the constructor. But the difference is mine I use a boolean to instead of 0 or 1 to check whether to return P1 or P2. So if true was passed in, I will return P1, and if false, I will return P2 instead.
Yeah, thank you. So, yep, this is another valid way of doing this. So you don't necessarily have to implement your ADDs like this, but if you were to be presented with something like this, you need to understand how it works, obviously, because this is an application of higher order functions, and it could be tested as a tracing question also. Yeah. All right, let's see if there's any other ways you're included. So be sure to look through the chat and see like what your classmates submitted, because it's very creative the ways you all use Python to create your abstract data type. So not only can you just implement your ADTs with tuples or lists or dictionaries. You can also use dictionaries if you learn dictionaries later. We'll also implement them with functions. Yep, with functions. And even if you implement them with functions, there are many different ways to like call your functions. Yeah, so you need to make sure you remember how all this works. Let's see if there's anything else interesting. All right, so let's move on to question 4a part 3. Okay, so finally we are using the selectors and constructors that you have defined. Define a function midpoint segment that takes a line segment and returns its midpoint. So the midpoint will be a point according to your implementation of your ADT. So can I see your solutions according to how you implemented your entire set of ADTs? So what this question is basically an ADT question, but it makes you implement 3 different ADTs, a point, a segment. Okay, actually point and segment only. But these two like work together and interact with each other. All right, let's have a Monish Manogaran. Can you explain your solution?
Hello. Yeah. So first I defined it, then point 1, I'll make it a segment, then point 2, I'll make it an end segment. Right. Then after that, it's just a matter of finding the midpoint of X, midpoint of Y, and then returning it by making it a point.
Yes, very good. So what you did here is you did not break abstraction. Breaking abstraction means basically like doing stuff manually, like creating a point manually when you already have access to the constructor. So when I believe most of you have started on mission 6, the road train hypothesis mission. So in that mission, we had a lot of ADTs like trains, stations, and stuff. And we had constructors, getters, and setters. And y'all would be marked down if you fail to use the getters and setters. You were to index the data type directly to whether be it to get information out of it or to change it, to edit it, or to create it. So basically when we have defined getters, setters, and constructors for extra data type already, you should continue using them because down the line in the future, you may update the data type in the future, which means you may change up the order of what you put in the tuple, or you add new fields and then switch it up. And maybe your getters work differently or your setters work differently. Then if you were to make that change, then everywhere where you've like manually created something, it'll all be wrong, right? You'll have a lot of bugs. So that's why if you use the getters, setters, and constructors all the time, if you use them all the time, then you just have to edit your constructor definition once, your getter definition, and you change it for every time you call it. So that's why we don't break abstraction. So notice here, when we return a point, you actually use the make point that we called like above, that we defined already. For the getters, notice that Monish didn't directly index the point. He used the getters to get the information out of it. Same for point 1 and point 2, and for here. So notice that no matter how he actually implemented his segment and points, this will still work. So like for any implementation, I can take any implementation or point, whether it uses a tuple or list or function, this will all still work because what it's doing is just it's calling the getters. So it could have been implemented anyway. So you don't have to know. So that's another thing about abstract data types is it's abstract. So the user doesn't need to understand how the function works. They only need to understand what the function returns, what it takes in and what it returns. So they are able to use it. So they don't have to understand how it works, which is represented here. So notice we could take any of the above implementations and this function will work for all of them. So that's why, so this doesn't matter. Let's see if anybody else did it differently. Okay, I see it's all about the same. Yep, everybody did it the exact same way. Okay, though, I have to highlight this one. Gangaharan. You returned a tuple of x-mate and y-mate. So this is what we call breaking abstraction. So what we did here is we calculated the x-mate, right? We used our getters to get a start segment and we use the getters to get a point. But what we did here is we failed to use the constructor to return an actual point. So what we can understand here is we are basically returning just a tuple. We're not returning a point, even though the point is represented by a tuple. This is technically just a tuple, and you can't really say it's a point because you've already wrote your constructor, and you don't have to understand how the constructor works. You just have to know that the constructor takes in your inputs and it returns a point. So you know that thing is a point, and you know what a point can do. You can use your getters to get the x coordinate of a point. You can use your getters to get the y coordinate of a point, but you don't need to understand how the point is implemented as a tuple or a list. So this is basically the theory behind your ADT. The user doesn't need to understand it. They only need to know the inputs and outputs and know how to use the functions that the developer has defined, the constructors, getters, and setters. So what he should have done here is instead of manually creating a point using knowledge of the implementation, he should just use the constructor make point like that. So this is expected to return a point and we don't end up breaking abstraction. Yeah. So for those that haven't finished mission 6, so be sure to keep in mind. Also for exams, you should not be breaking abstraction. So when a question defines like constructors, getters, and setters, or like in sub questions, you define your own getters, setters, and constructors, do not break abstraction by manually indexing your data types. You should always call the getter, always call the setter, always call the constructors. So yeah, this should work. All right, let's move on to the last question. Okay, we have just enough time. Implement a representation for a rectangle using however you implemented your points and segments. So you need to create constructors and selectors. Selectors are basically getters. Can I see your implementations? So this question actually requested you to come up with 2 different ways of implementing. So let's just go through all the different ways that you came up with. Well, I realized this question was in the PDF, but not in the actual cosmology tutorial. I think that was a bug. Yeah, if you all had actually looked at the PDF, this question will be out. Okay, I can see some of you actually found it. All right, while we wait for more representations. Okay, Julius, can you explain how you represented your rectangle?
Hello.
Hi.
Yeah, it's represented by just the length and the height. Yeah, so it's being constructed into a tuple. So the length basically just returns the length, the first index in the tuple, then the height returns the second one or index one.
Yep.
Then area just use the
constructors to multiply the height and length. Then perimeter is just 2 times height plus length. Yeah.
Yep, very good. Thank you. So, okay. So very good. So here you did not break abstraction. So note in exams and your missions, like when you have your constructors and your getters, even with some functions that take in your data type, you must make sure that you do not break abstraction within these functions also, right? You also go on you for using the getter that you have defined above in the implementation of your area function and your parameter function. So if you had done something like this, let's say you manually index it like this will be breaking abstraction. Because this will only work if you know exactly how the underlying rectangle had been implemented. And this is generally considered bad coding practice. Okay, let's see if you all have any different ways. Okay, Ethan Ng, how did you implement your rectangle?
Okay, so at the top layer, I define perimeter and area first, which uses the functions width and height. But at this point, we just assume that width and height like do their job, and we don't need to know like how it does its job yet. We just assume that it correctly calculates the width and height of rectangle. Then we go to the lower level where I define like the construction of a rectangle, which takes two properties. One is the lower left point P1 and then the upper right point P2. Then it returns a function which basically takes any function and applies that function to P1 and P2. So that function can be like, for example, the width and height below, which basically just correctly calculates the width and height of the rectangle by taking the absolute value of the difference in the x and y values of the points. Yes.
Right, thank you. So yeah, so this implementation of rectangle. So notice that this implementation actually takes in different inputs. So up here, we represent our rectangle using its length and its height. But over here, we actually represent our rectangle using two of its points. So like it affects what sort of information you actually store on the rectangle. So this implementation stores only the length and height, which works for this question because all the question wants you to do is be able to turn the area and perimeter of the rectangle. But this representation additionally also allows you to obtain the location of the rectangle. So this is a minimal solution where you only keep 2 points, the lower left point and the upper right point. So you don't actually have to keep the other points, the upper left and the lower right. You don't need those points because you can derive them from the definition of rectangle. You know what a rectangle is, so you know if you know that this point is the lower left and you know that this point is the upper right, you can derive the other points just by like minusing off. But since this particular question only needs you to find the area, so you can use like various transformations to find the length and height before you do your math and return the area and perimeter. So like different questions may require different requirements. So whether or not your extra data type needs to keep specific information, like needs to keep track of its height or specifically its location, like different ways to work differently. So we have another way over here by Ganga Haran. So can you just briefly go through how you represented your rectangle?
Oh, hello.
Hi.
Okay, so the input for the function make rectangle is basically the four corners of the rectangle, and then I um just made I just okay, I just made like 4 variables. Two of it are the two possible lengths of the rectangle. The other two is the two possible breadths of the rectangle. And then I defined a local function called length where it finds the segment where it finds where it finds the length of a segment, and then it will return like a tuple which tells you the four lengths of the rectangle. And then the other two functions below are perimeter and area functions, where the perimeter function is just the sum of all the sides of the rectangle, and the area is just the sum of the item with index 0 and item with index 2, which is just the length times breadth of the rectangle. So yeah.
All right, thank you. Okay, so this is another creative solution. So the constructor for his rectangle actually takes in 4 points, the 4 points of his rectangle, but it doesn't actually store those points. It stores the side lengths actually. So the two lengths and the two breadths. So actually what he could have done here is you only needed to store one of them because it will always be the same. The top length and the bottom length will always be equal because that's the definition of a rectangle in math. And for our definition in programming, we can simply just store what we need. So just a length and a breadth. So it's quite similar to the above solution, but just that instead of taking in the inputs as the length and height, we take in the inputs as the points. Yeah, so depending on your question requirements, and if they ask you to implement an ADT, you need to like understand what you need to do with the ADT, and from then you can like derive what you want to store, what information you want to store about your ADT. So yep, that brings me to the end of the tutorial. It's 9:02. You all are dismissed if you have no further questions. So bye. Hi, must I know L'Hopital's rule? No. Like generally for these complicated math formulas, the prof would write it out. Like if he were to come up with a question and ask you to implement L'Hopital's rule, you obviously put out the math formula. For midterms, is a cheat sheet allowed? Okay. Okay, midterms. Okay, has Prof said anything about it? I think you should you can check with the lesson plan. Otherwise, you can ask Prof during his recitations or lecture review. Because it may change year by year, but across the years, cheat sheets have been allowed, but you need to double check with Professor. I can ask him right now if you were to come back. We are asking this regarding calculating time and space complexities. Okay, it won't be that difficult. Yeah, we will not have such a difficult question where you need to know L'Hopital's rule to calculate the time space complexity. Right, okay, bye. I'm gonna stop the recording here.